Good morning. Can you guys hear me okay?
Yeah.
Can you all hear me?
Yeah.
Oh, okay, good. Okay. I think the first thing I want to do is answer questions you may have on the homework. And then I'm going to go through chapter 34. And so that, boy, this is a weird week. I'm going to use 1 hour on Friday to lecture on relativity and the lab on Monday to lecture on relativity. And so our last exam is going to be based on chapter 34 and a little bit on relativity. Okay? So it won't be a long exam. Okay, so what are your questions on chapter 33 homework?
Chapter 33 is homework 13, 12?
Homework 11.
Oh, the one that you moved?
Yes.
Oh, I just finished that. Well, I came yesterday and asked you the questions I had.
Okay. Or just, any questions before the exam, I guess I figured this would be a good time. Because I got 1 or 2 emails regarding questions on this homework assignment. So I figured I can use this time now to answer questions. Otherwise, I'll go on and talk about 34.
I have a question.
Okay.
I don't remember which question it was exactly, but it was a question about like the maximum voltage on a capacitor and the inductor.
Okay.
Number 12.
Oh yeah, number 12, I think. Do we have to just take the derivative of the voltage and
Yes.
and then set it here?
Yes. Anytime you need to, anytime you need to maximize a function, we use the techniques you learn in calculus, right? To take the derivative of the function with respect to the variable and set the derivative equal to 0. So in that particular problem, in number 12, were you looking at the voltage across the capacitor or the inductor?
I think it was both. I was just confused because I thought it's the same as resonance frequency, but it wasn't.
And that's why I gave this problem, because it's not.
Yeah.
Everybody misunderstands that. At the resonance frequency, so at resonance, I sub m is maximized, and V sub r is maximized.
At resonant frequency, the voltage across the inductor and capacitor is 0, right? In a series?
At this frequency?
Yeah.
Yeah, the sum of the two voltages equals 0.
Oh, the sum is 0, but the voltages together equals... Okay. Well, because number 18, it was like they were supplied voltage, right? But that's a parallel.
That's a parallel circuit, yeah.
Yeah.
Yeah, so at resonance, I sub m is maximized, V sub r is maximized, but V sub c and V sub l is not necessarily maximized. Actually, it's not only if r is 0. And so if you want to look at the voltage across the capacitor, for example, or the maximum voltage across the capacitor, it's going to be your total current times X sub C, your capacitive reactance. And your I sub m is going to be V sub m over your impedance And I still haven't written my expression explicitly. Oops. I still haven't written my expression explicitly, but now I will. Their impedance looks like this. Okay, so now you want to maximize that function. You want to find the frequency, the omega, at which this function is maximized. And so yeah, you got to take dw, I'm sorry, dv sub c over the omega, set it equal to 0, and solve for the frequency, the angular frequency that makes this thing 0. So what I recommend, because this actually looks kind of complicated, what I would recommend is I would pull out the 1 over omega term out of here like we were doing when we were analyzing the resonance circuit, when we were analyzing the power. I would pull out the omega because then the function becomes a lot simpler. If I pull out the omega and I'm going to pull out the L, I get the following. And that omega will cancel out this omega, for the capacitor at least. And now when you take the derivative, you get a nicer expression to differentiate. In fact, for the capacitor, it's very nice to differentiate this. So for the capacitor, you're going to get something like this. Now when you take the derivative of this respect to omega, this is a little bit easier. If you leave it in this form and take the derivative, it's going to be a lot more work. Does that make sense?
Yeah.
Okay. Other questions on the assignment? By the way, those of you who are going to take 215 next semester, you're going to do the driven damped harmonic oscillator, where this is going to represent the amplitude of the oscillations. And you'll find that at resonance, the amplitude is maximized, but the kinetic and potential energy are not maximized at that. I'm sorry, let me rephrase that. The potential energy is not maximized at that energy, at that frequency. You see the same kind of things there too. Okay, so be aware that at resonance, this is maximized and this is maximized, but not these two. And a lot of times that's kind of, students don't see that. Okay. And when you do the LRC lab and you're doing the measurements, you're going to get some weird results, right? Because what you're going to get, you're going to be measuring the voltage across the resistor, the voltage across the capacitor, and the voltage across the inductor. And these voltages might be bigger than this one. You'll find instances where these two voltages are bigger than this one, which will be strange. Energy
Because they're in opposite direction. They
Yeah,
kind of like cancel each other out partially.
that's right. I mean, energy will still be conserved. Yeah, because these two are in opposite directions, they have a cancellation effect, right? In other words, they're 180 degrees out of phase with each other. Yeah, so for number, I purposely asked number 12 because students misunderstand what this means. Other questions? So I was going to lecture on solving this. I was going to do a lecture solving this differential equation for the RLC circuit. But I think what I'm going to do is I'm going to create a video for you to watch. And the information in the video will probably also help you with some of the things you'll have to do in the lab. Okay. And I'll try to break it up into a couple of videos so you don't have to watch one long video. I'll talk about the solution to this equation, then I'll talk about the power equation, and I'll talk about the current equation. Any other questions, concerns regarding the exam on Friday?
Ooh, is it hard?
Is it hard? I don't think it's as hard as the other ones, mainly because the problems get quickly unwieldy in this unit if you try to use non-standard problem. It's actually very difficult for me to use non-standard problems on this exam because they can get very difficult, especially if I have you calculate mutual inductance.
So what you're saying is to just review the homeworks and you should do good.
Yeah, I mean, I'm still going to try to give you problems that are hard to Google, but they're not going to be as non-standard as the first three exams. Let's put it that way. And when I give this exam in class, you'll find students that still mess up on this exam. So I don't want to say it's an easy exam. I'm still going to say it's a challenge. I'm still going to say it's a challenging exam, but it's probably not going to be as probably as challenging as the other ones have been. At least I think. Okay, I guess you'd have to ask the class that just took it and see what they say.
Yeah, they don't seem too happy.
They don't seem too happy? Really?
Yeah.
Okay.
Patrick says that he hopes you offer corrections.
Okay, I guess maybe I was wrong. I didn't think that was that difficult, but okay. Now that gets me worried. That's not what I wanted to happen. And we'll see how you guys do. Okay, so I'm going to say a few more things about chapter 34. I want to cut chapter 34 short. Just 1 second. You go back to where I was at last time.
Amperes.
Yeah. All right. So I want to finish up chapter 34, and I'm gonna, like I said, I'm gonna cut it a little bit short. I'm only gonna focus on waves and the energy. There's a section on momentum and radiation pressure. I just don't have the time to go through it. Although I do want you to read through it briefly. And most of the problems on radiation pressure are just plug and chug homework problems. Okay. But for the exam, really what I want you to focus on is the electromagnetic waves itself and energy. Okay. So last time I introduced the displacement current, and which really was an important discovery by Maxwell because it made Ampere's law consistent. It also said that time-varying electric fields generate magnetic fields. Kind of makes Maxwell, Ampere's law and Faraday's law kind of symmetric, because Faraday's law says time-varying magnetic fields produce electric fields. So Maxwell took all these equations and worked with them. And like we said last time, upon working with the equations, he was able to predict electromagnetic waves and their properties. So what are some properties? Well, electromagnetic waves can interfere. They can combine to form a bigger wave. They can bend. It's called refraction. They reflect. He was able to make all these predictions from his equations. Furthermore, he was able to show the following properties of electromagnetic waves. If a wave travels in the y direction, in the y hat direction, then the dot product of y hat with the electric field and the dot product of y hat with the magnetic field is zero. That means that the electromagnetic waves travels perpendicular to the electric field and magnetic field. Furthermore, he showed that the cross product of the unit vector in the direction of travel of the wave with the electric field gives you some constant times the magnetic field, and that constant is the speed of light. And of course, the cross product of the direction of travel of the wave with the magnetic field is minus E over C. And he also used these equations to derive some of the laws of optics. His prediction, his equations predicted that waves travel at 3 times 10 to the 8th meters per second, which agreed with what was known already and with what Hertz did in his experiments. Hertz was able to verify the speed of light that he predicted, but also some of the behavior of waves that he also predicted with his equations. Look at the equation for the speed of light in a vacuum. It's 1 over the square root of epsilon naught times mu naught, which is kind of interesting. And he was also able to predict electromagnetic waves from accelerated charges. So what I'm going to be doing the next few minutes, I'm not going to really be, a lot of this stuff is kind of hand waving because the math can be kind of complicated. I'm also summarizing results just because of time. But what I want you at least understand is the overall properties of waves. So one of the solutions to his equations are called plane wave solutions, which assumes that you're far away from the source of the electromagnetic waves. When you're far away from the source of electromagnetic waves, and the source, we're assuming they oscillate sinusoidally, they predict electromagnetic waves that oscillate in a plane. And since the source is periodic, the waves will be periodic. The picture that you see shows the oscillation of the electromagnetic field and the oscillations of the magnetic field. The electric field and magnetic field oscillate in phase, but they are perpendicular to each other. And the direction of travel is perpendicular to both. The distance in which the wave repeats itself is called the wavelength. So the distance between peaks is the wavelength. Okay. The time it takes to get from one peak to the next is the period. And if you take the wavelength over the period, that gives you the speed of light. And 1 over the period is also known as frequency. So we write the speed of light as c equals f lambda. And when you take 215, you'll see equations like this. So one of the important equations here is c equals f lambda. Speed of light, frequency, wavelength. Okay. And then another important equation again is the angular frequency, omega. That's the rate at which that phase changes. And then we introduce something called the wave number, k. K is called the wave number, it's 2 pi over lambda. Because this is related to the momentum of a wave. That's why we define it as k. It's basically it's related to the number of waves per cycle. And then omega over k, you can see that omega over k is the speed of light. And can you show that? Well, I take this equation, and multiply the denominator by 2 pi. That's omega. That's 1 over k. The quantities Emax that you see in the figure, or the Emaxes, is the amplitude of the wave. And the same thing for Bmax, it's the amplitude of the magnetic field vector. Normally we describe the wave in terms of the electromagnetic field, and then we just got to assume that the magnetic field is going along with it. It's perpendicular to the electric field and in phase with the electric field. Okay. Now, where do those plane waves come from? They come from solving Maxwell's equations. If you solve Maxwell's equations, if you manipulate Maxwell's equation when you're really far away from the source, you get an expression that looks like this. And we're doing this problem in a one-dimensional world. And you get similar equations for the magnetic field. So this is the wave equation. For E when you are far away from the source. And when you're far away from the source, you can always set I equals 0 and Q equals 0. Okay. And one of the solutions are plane waves. The general solution of these equations have that form, where the electric field is some function of position and the product of c times t, where the plus sign represents the wave traveling in the minus x direction, and the minus sign represents the wave traveling in the plus x direction. The simplest solutions of that form are the plane wave solutions, where you have an oscillating source that's really far away. If I factor out the k, I will get, if I factor the k out of here, I'll get that. Okay. I'm writing it this, I mean, you got to write it this way in this particular case because this whole thing has to be dimensionless. In the case of sines and cosines, this has to be dimensionless. Whatever you're taking the cosine of has to be dimensionless. But you still have this form in there. Okay. Now, our job here is not to get this from this. Okay, your job is not to be able to get this expression from this guy. Your job is to be able to show that this satisfies that equation. How would you do that? How do you show that this is a solution?
Take the second derivative?
Yeah. So what you should do is take this equation and stick it in here and stick it over here and see if it works. I'm not going to do that here because I got to take two derivatives, which takes a little while. Okay. So your job is to be able to do that. And there's also an equation for the magnetic field where you replace this E with a B.
Is it plus and minus though? So we take a derivative?
That's a good question. If the wave is traveling in the positive x direction, it's a minus. If the wave is traveling in the negative x direction, that's a plus. So plus in negative x direction, minus in positive x direction. I don't know if you've ever done, if you had in pre-calc, maybe you do these things called transformations. When you transform from one reference frame to the next, and that's where you get to see, because when a wave moves in a particular direction, you can see it as you can use a transformation to a new coordinate system. And then you can see why this one's a minus when it's in a plus x direction. Okay, so these are the solutions. These are the problems we want to look at, the systems we want to look at. Okay, because most sources are very sinusoidally with time. And then, yeah, your job is to be able to verify that those are the solutions. Same thing with the following. Do those equations satisfy the wave equation? By the way, we already answered the first question in the notes. Let me magnify this. Sorry, let me make this bigger. I already answered the first question that the electric field and magnetic field are in phase. But do those equations satisfy the wave equation? And the answer is yes, but how do you prove it? You got to take those equations and stick them into the wave equation. Okay, even that, but that's not due to a sinusoidal source. Okay, those are not plane wave solutions. That's due to a different source. It's really far away from the observer. And again, in the interest of time, I'm not going to go in and plug that into the differential equation. That one's worse to take two derivatives of. So let's talk about the values of lambda for electromagnetic waves. Lambda spans a large region. By the way, I did get this picture from the Advanced Light Source at Berkeley. They have that's where this picture came from. I should at least credit them. At least they display themselves in there. So electromagnetic waves come from a broad range of frequencies. And as you can see, the frequencies and the wavelengths span, well, the wavelengths span from values bigger than 1,000 meters to values smaller than 10 to the minus 12 meters. And really, we should talk a little bit about how we categorize these waves. And there's no distinct boundaries between different types of waves. So if you look at that, in the range from about 10 to the minus 1 meters, which is about 10 centimeters, to about 1,000 meters or greater, generally we call those radio waves. And those correspond to frequencies around 10 to the minus 9, 10 to the minus 10 hertz and below. Microwaves fall in the range of 10 to the minus 1 meters to 10 to the minus 4 meters. And notice they overlap with infrared. And you see the frequencies are getting higher. We're talking about 10 to the plus 9 to 10 to the 12th hertz. The infrared range goes from about 10 to the minus 3 meters to 10 to the minus 6 meters. Actually, into the 10 to the minus 7 meters. The most interesting one to us is because we can see is the visible regime, and that's the smallest range. Look at that range. Let me write it on the board. The visible range. The visible range spans from 400 nanometers to 700 nanometers. This is red. This is violet. Okay. 400 times 10 to the minus 9 meters to 700 times 10 to the minus 9 meters. So these are less lower frequency, that's higher frequency, because F is C over lambda. So if you want to look at the frequency range, we're going to do the following. We're going to take, find the frequency, it's C over lambda. And we're talking about 10 to the 14th hertz. That's the frequency range. Then you go to ultraviolet range, which goes all the way up to about 10 to the minus 8, high 10 to the minus 9 region. And it overlaps with soft X-rays. And soft X-rays overlaps with hard X-rays, and then you have gamma rays. So, for example, how do you tell the difference between what's a hard X-ray and a gamma ray, for example, as you see on that list and that figure? Generally, gamma rays are thought of as originating from the decay of a nucleus, and hard X-rays are considered from originating from accelerated charged particles. Now, the bottom scale represents energy. Where does that come from? How How do you describe the energy of a wave? Well, you'll learn this in Physics 215, that the electromagnetic waves can be described in terms of these particles called photons that have no mass. And these photons have energy, h times frequency, or h is called Planck's constant. H is 6.626 times 10 to the minus 34 joule seconds. It actually has units of angular momentum. Okay, so the energy of a photon is given by this value. And electromagnetic waves that travel through space consist of a large number of photons per unit volume or per unit area, depending on how you're just trying to describe them. If you're describing them in terms of intensity, you would talk about the number of photons per unit area per unit time. Okay? So you can relate the intensity of a wave, and I'll talk about intensity a little bit, in terms of the number of photons per unit area per unit time. Okay? So that scale that you see on the bottom, this is in joules, you got to convert it to electron volts, represents the energy of a single photon. But an electromagnetic wave will consist of a lot of photons. So for example, when we talk about visible light, you're talking about energies of around 2 electron volts. Whereas X-rays, you're talking about thousands of electron volts. Any questions on this? As someone who's taken science, this is something you should remember as you go away from this class. It's basic information that you should take away from this class, knowing what the electromagnetic spectrum is. And if you've had chemistry, you've probably seen something like this, a picture like this before. Something you should know. So, how are electromagnetic waves produced? And I think I talked about this already, but electromagnetic waves are really produced in 2 ways. Free charges accelerate. Accelerating electrons or accelerating protons will produce electromagnetic waves. They're basically vibrating charge. Okay, vibrating charge will produce electromagnetic waves. Okay. Just give me a second here. And so, like for radio waves, we're talking about vibrations of the order of 550 to 1600 kilohertz. And then for FM is 88 to 108 megahertz. Another way electromagnetic waves are produced is from transitions in atoms and molecules. And they occur from a higher energy state to a lower energy state. And the visible light's of the order 10 to 14 hertz. So these are the only 2 ways electromagnetic waves are produced. Either accelerated charges or transitions in atoms or molecules. And I should say within the nucleus too. Any kind of transition. So, if you have, let's say, a wire, in fact, let's say I have 2 wires. This is called, I'm going to call it a dipole. And these two charge alternately. Let's say this, when this is positively charged, this is negatively charged. And this thing, as this thing goes through a cycle, the electromagnetic field propagates perpendicular to the oscillation of the dipole. So imagine this is hooked up to an AC circuit. So the charge on here goes between 0 and some maximum and then reverses itself. And that's going to produce an electric field that goes all the way around this thing, that propagates outward. And this is not really the correct picture. Would be the correct picture if you're really far away from the source. But I'm drawing this just so that you can kind of get an understanding. A better picture is what you see in that slide, at least near the source. Since you have charge going up and down this way, by Ampere's law, you know that there's going to be a magnetic field circulating around that, as you see in the figure. So that red represents the magnetic field, and then the blue represents the electric field. And the energy is transmitted perpendicular to both the electric field and the magnetic field. The electric field acts like a particle, or electromagnetic waves act like a particle because they carry energy, they carry linear momentum, and they carry angular momentum. When you shine laser light on an atom, you can change the state of an atom. You can also change its momentum. You'll change its linear momentum too. Its angular momentum too. So they do have particle-like properties in the fact that you can change the energy of another particle with waves. You can change the linear momentum and the angular momentum. Of course, we don't really talk about this until you get to the end of Physics 215. This shows the radiation pattern for an oscillating dipole. There's no energy transmitted along the axis of the dipole. It's all perpendicular to the axis of the dipole. How do I solve for this? This is a very difficult problem. We don't do this. We just tell you this. We're doing hand waving at this point right now. So the last important thing I want to cover is the flow of energy. I want to talk about the flow of energy through a thin box. So let's imagine we have plane waves, plane electromagnetic waves, flowing through a thin box. And for the purposes here, I'm going to assume that the electric field is going to have the same value over the surface area of the box. And let's say that the box has thickness dx and surface area A. And you have an electromagnetic field traveling perpendicular to that surface. Okay, so the oscillations of the electric field are up and down, and the magnetic field are side to side, but the direction of travel is normal to the green surface. And that's, you see, by the speed of light c. So I want to look at the amount of energy that's going per unit area, per unit time. I want to look at the amount of energy per unit area per unit time. The amount of energy that's going per unit area per unit time through that box is the rate at which energy flows through there divided by the area. So du dt is U is the total energy. Du dt is the rate at which energy flows through the box. And then dividing it by A gives you the energy per unit area per unit time. But U, or du, is the energy density for the electric field plus the magnetic field times this area times the thickness of the box dx. In other words, is U total times A times the x. And this is what we talked about in a previous chapter, these. Remember that U sub E, let me go on the board. U sub E is 1/2 epsilon naught E squared, and U sub B is B squared over 2 mu naught. And at any time, the total energy is the sum of these two, or the total energy density is the sum of these two. And if the energy is conserved, then the total energy, or the total energy density, can always be written in the following way. Or this is the maximum value. Or you can write it in terms of the electric field too. And then du dt then is U total, times your area times dx over dt. Well, dx over dt is a velocity, but since we're talking about the velocity of light waves, this is the speed of light. And so we get the total energy density times the area times c is du dt. So if I divide this by A like I did before, this is the total energy times the speed of light. So the total energy then is, and I think what I wrote on the board was, I made a mistake with my, I left a 2 in there on the board. So the total energy just B max squared over mu naught. Because if you write the two terms for the energy density, and this is going to be B squared max over mu naught times C. And if you use the relationship, let me go back up here. If you use the relationship that E is C times B, you can write this in terms of a B and an E. You can write this way too. Or you can write this in terms of E and B by using this relationship. Either way. So in the notes, I wrote it in terms of E and B for a particular reason. I'm writing it in that way for a particular reason because E and B are perpendicular to each other, and they're perpendicular to the direction of travel. And what I want to do is define a vector that not only tells me the direction of travel of the wave, but how the energy is carried by the wave. And so I'm going to define this vector, E cross B over mu naught. This vector points in the direction of travel of the wave. In fact, E, B, and the direction of travel form a right-handed coordinate system. And they also tell me how the energy per unit area period of time is flowing. And we call this the pointing vector. So the pointing vector tells you how the energy is flowing per unit area per unit time. Okay. But it also tells you the direction the energy is going to also. Okay, so denoted by the letter S is equal to E cross B over mu. mu naught. And its magnitude, since these two guys are perpendicular to each other, it's just E times B over mu naught. And these are the vectors. Okay. Now, if you take an average of this over a cycle, if you average this over a cycle, obviously if you average a cosine function over a cycle, if you average a cosine function over a cycle, you get, I'm sorry, you have cosine here and cosine here, that gives you cosine squared. You take the average of cosine squared, that gives you 1/2. So a lot of times we talk about the average over a cycle. And the average over a cycle the magnitude of this thing is called the intensity. And so, you know, again, like I said, since you're going to take the average of cosine squared, you're going to get 1/2. So the intensity is called the power per unit area, the energy per unit area per unit time, and that's the same thing as S average. And you can just write it as E max, B max over 2 mu naught. This is the intensity of a wave. It's the power per unit area. And since S average is U total times C, then I is C times U average. Now, going back to what we were looking at in the previous slide, go back. This picture assumes that the electric field is constant over the area. What if the electric field was not constant over the area? How would I get du over d? How would I get u? Or how would I get du dt? If E was not constant, in other words, it varied over the surface, then I'd have to integrate over that surface. And my total energy then would be the integral of S dot n dA. And that would give me the rate at which energy is going through the surface. I'd have to change my A to a dA, then integrate S over the area. Okay. So now we talked a little bit about the Poynting vector. I'm going to do one example and then I'm going to end it here. This is a fairly standard problem involving electromagnetic waves. This is definitely a problem you want to know how to do for exam 5. Okay. So you want to write out the formula for the electromagnetic field that specifies the waves with the following characteristics. You have the direction of travel in the minus x direction. The frequency is 10 to the 8th hertz. E is 50 volts per meter. And E is perpendicular to the z direction. Let's calculate the wavelength, the average energy density, the average Poynting vector. Okay? And I think I'm not going to go beyond this point in the chapter. Just in the interest of time. Okay, so we have electromagnetic wave. F is 10 to the 8th hertz. E 50 volts per meter. And it's in the minus x direction. And it's perpendicular to the z direction. So the oscillations are in which direction then? If it's traveling in the x direction and moving perpendicular to it's moving in the minus x direction and it's oscillating perpendicular to the z direction, which way is it oscillating?
Y?
It's got to be y, right? It's going to be
Yeah.
it's got to be plus or minus y. Let's find the wavelength. Since c equals f lambda, lambda is c over f. So c is 3 times 10 to the 8th. I mean, it's like 2.999, etc., but we're just going to write it 3 times 10 to the 8th. Frequency is 10 to the 8th hertz. So this is 3 meters. Omega is 2 pi times the frequency. So it's going to be 2 pi times 10 to the 8th. K is 2 pi over lambda, 6.28 over 3. And I want to use the following form for the electromagnetic field. know it's going to be in the j hat direction. Actually, it can be in the positive j hat direction or the negative j hat direction, because I wasn't very specific there, right? I just said perpendicular to the z direction. So I would choose either answer. So when I write the electromagnetic field, I can write the following. And now I'm going to suppress the units because I don't have space here. But really, this can be either plus or minus because I wasn't specific. I wasn't specific enough. So I would accept on an exam either one of those two. Either plus or minus, I would accept. Okay. So let's say I choose plus. Now, how do I write the magnetic field? Well, the magnetic field, we know that E over B is C. So that means B. So the magnitude of the magnetic field, B max, I'll use a different color. B max is going to be 50 volts per meter over 3 times 10 to the 8th. And this will give you 1.67 times 10 to the minus, hold on a second, 7 Tesla. So the magnetic field is going to be 1.67 times 10 to the minus 7 Tesla cosine of 2.09x plus 6.28 times 10 to the 8th t. What direction? Well, it's got to be perpendicular to both that and this, so it's got to be the k hat direction.
Yeah.
Now, I got to be careful. Okay, I got to be careful because the electric field, the magnetic field, and the direction of travel form a right-handed coordinate system because S E cross B over mu naught. So the direction of this is in the direction of travel. I got to be careful here. So let me draw a right-handed coordinate system. If I choose a plus sign here, I got to be careful with the sign here. So let me draw a coordinate system. I'll call this Z. Let's call this X, Y, Z like that. Okay? So if the electric field is in the j hat direction and the wave travels this way, okay, the wave travels this way, the electric field this way, then if I take the cross product of the electric field with the magnetic field, and we said that the magnetic field points up, does the cross product make sense? The E cross B. Am I right or wrong when I do E cross B?
You got to point down, right?
I got to point down, right? I got to put a minus sign here. Now, if I chose this to be negative, then this would be positive. Does that make sense? Because I have to agree with the direction of travel of the wave. The direction of travel of the wave in the minus x direction. Now, how do I get the pointing vector? Well, I'm going to take, well, if I just want the average pointing vector, I'm going to take this times this divided by 2 mu naught. Okay, let me get my eraser somewhere. Oh, here it is. S average is going to be E max, B max over 2 mu naught. And we know that it's going to be in the minus I hat direction. Okay. So then I just get my calculator. I take this times this. B sub m is mu naught is I get that. Joule per second is a watt.
And this is when you're assuming that the magnetic field is maximized? Oh, right, because that's what it is, B max. Okay.
Yeah, B max. Yeah.
Okay. Because I was seeing, because obviously you have an equation with respect, like it's in T.
Yeah, I took the average, right? And the average, that's
Yeah.
where this 2 comes in, right? This is the instantaneous value, but the average value gives you 1/2 because when I take the product of the two, the average of cosine squared is 1/2.
Yeah.
Okay. And then I can also get u sub t. All I got to do is take b squared over mu naught, b max squared over mu naught. So basically, I got to take this guy squared. Obviously, there's other ways to write it. I'm running out of space. And that'll give me 1.1 times 10 to the minus 8 joules per meter cubed. I need more board space. Okay. So this has all the information about the electromagnetic wave. Now the only thing I don't have is the energy of the photon, but then we're not talking about photons here yet. Okay. And so these are the kind of things you want to be able to calculate. Actually, let me just say one more thing about waves. You know, how do these waves propagate? Okay. Just like if we're talking about a source of waves, let's say a periodic source, a periodic disturbance that varies sinusoidally with time. Imagine taking your finger and dipping it into the water sinusoidally. You're going to get these waves that spread out, that ripple outwards. Okay, so just imagine a charge oscillating sinusoidally with time to produce electromagnetic waves. The waves will be spherical in form, just like the waves in the water, like when you drop a pebble in the water, except this is periodic. And the waves get bigger and bigger. The energy in each wave assuming there's no resistive losses, is the same. Okay? The energy in each wave, so when you look at this picture, those circles that you see are called spherical wavefronts. The energy in each sphere, I know it's two-dimensional, it's a circle, but think 3D. But the energy on each sphere is the same. The only thing is the spheres are bigger as you go farther away, so the energy per unit area decreases. The pink circles represent either the peaks in the waves, how they travel outward. So you can describe a wave in terms of a wavefront, or you can describe a wave in terms of a ray. Now, as you get further and further away, what do the wavefronts look like? As the radius gets bigger and you're looking at a small piece of that sphere, the wavefront's going to look like a plane wave. It's going to look planar. And the energy is distributed over the surface of the sphere. So when you get really, really far away from the source, the wave will look like a plane wave. That's why we talk about the plane waves, because we're assuming we're far away from the source. Now, as the wave gets bigger and bigger, or as the sphere gets bigger and bigger, remember the energy stays the same. What happens to the amplitude of the wave? Well, the amplitude of the wave, the energy in the wave depends on b squared. Okay, the amplitude of the wave depends on the square of the energy in the wave depends on the square of the amplitude of the wave. You can either write it in terms of e squared or b squared. So the energy in the wave depends on the square of the amplitude. So as the energy is distributed over a larger sphere, what's going to happen to this amplitude? What must happen? Well, the amplitude has to go down to conserve energy. Since the area goes as r squared, and the energy goes as amplitude squared, then the amplitude has to go down as with radius. The amplitude has to decrease with radius. When we are really far away from the source, so in other words, if you plot amplitude as a function of position, it does this. And as you notice that when you're really far away from the source, you're asymptotically approaching zero. Whether you go from here to here, does the amplitude change much?
No.
No. So when we doing problems when we're really far away from the source, we assume that the amplitude stays constant. That's something you need to think about, because a lot of times we don't think about that. But you look at a lot of the problems in the physics books, when we do plane waves, we're assuming we're so far away from the source that the amplitude doesn't change much when you go, let's say, from this point to this point. But in reality, the amplitude decreases as 1 over r.
And this is like what determines like how far we can see in the universe or galaxy, etc.
Well, there's other effects, but yeah, the intensity of light decreases, right?
And so we had to build just more powerful equipment to be able to see further because the amplitude's so low of the waves coming in.
Yeah, and that's why we work with intensity instead of the actual energy, because if you have a detector, and I'm going to assume spherical waves, okay, because it makes the math easy. let's say I have waves traveling outward, right? And each one of these has the same energy. And I'm over here with a detector. The detector area is A, okay? And it's going to measure how much energy it collects from the source here. Well, it's not going to collect all the energy, right? It's going to only collect a certain portion of it. The amount of energy it's going to collect is basically the amount of portion that's in here. So I got to take the total energy, right? So I'll take the total energy, and then we're going to look at the rate at which energy is transferred. So I'm going to look at power per unit area times A. This is how much energy per unit time it's going to be collecting at that point. It's not sampling all the energy from the source, but it's sampling a small portion. So this is the intensity. So the intensity is the power per unit area radiated from the source at that distance. This guy decreases as you get further and further away. So like you were saying, the intensity decreases as you get really further away from the source. So I need more powerful equipment to be able to detect stuff that's further and further away. Does that make sense?
Yeah.
Okay. And so this is the intensity, the power per unit area. And the intensity I talked about, right, it's U average times C. Are we okay with that? I just wanted to mention it. And in 215, you're going to see this discussion when you talk about mechanical waves, and you're going to talk about optical waves again. You're going to talk about the behavior of waves, electromagnetic waves in physics 215. Again, there's a lot of hand waving there too, like I'm doing today. Okay, I'm going to stop here. So for the exam, you're just responsible up to this point. Okay. So
And we have a homework due on this, right?
I'm sorry?
We have a homework due on this, like material, right?
Yeah, there's a homework assignment on this material. It should go pretty quick. And in fact, I'm going to go through and remove some questions unless people started on it already. Let's make it a little bit shorter. Okay? So I'm going to stop here because my office hours start in 10 minutes and I need to eat lunch within that time. I'll talk to you guys later, and I might I'm trying to see if I can hold a study session for you guys maybe Thursday if you have questions.
Awesome.
Okay? I'll probably try it like Thursday evening. All right, we'll talk to you later then.